Good morning, everyone. I'm really excited to present to you some of the work that we're doing in our Smart Reservoirs team, which is composed of ecosystem scientists, computer scientists, social scientists, and engineers that are working really closely together to develop drinking water forecasts for water utility managers. I want to do a special shout out to Quinn Thomas, who developed our data simulation workflows, and Renato Figueroa, who's a graduate student with the Schmond, who developed the underlying Cyberinfrastructure for our project. At a high level, what we're doing is taking data that are streaming from water quality sensors embedded within a reservoir, securely and wirelessly to the cloud, where they're being used to run ensemble models that are generating iterative forecasts, probabilistic forecasts every single day. And for example, on this particular forecast, we're predicting that there's a 95% chance of high iron in your drinking water on Thursday. We're generating these forecasts and co-developing them with managers that oversee the reservoir called Falling Creek, which is a drinking water source for the city of Roanoke, Virginia, which is located about 4 hours southwest of here. Falling Creek has high algal blooms, as you can see here in this picture. It also has high metals, which are the focal variables that we're trying to develop forecasts for managers. The glue to our Cyberinfrastructure is called IPOP, which stands for Internet Protocol Over Peer-to-Peer Software, which is a type of open source software that's developed by our colleague Renato Figueroa. Within our forecasting system, we have sensors, which are connected to data loggers, which are connected to sensor gateways, which essentially are miniature computers, which are wirelessly streaming the data to the cloud. Within the cloud, we have an overlay virtual private network, or VPN, which is part of the IPOP landscape, which allows all of those different components to seamlessly share data amongst each other and securely. Within this landscape, we're able to do data processing, automated QA/QC, as well as modeling. And then from the servers, all the data are pushed to GitHub, and we're also streaming data directly to the Environmental Data Initiative, or EFI, for publishing. To show you one day in the life of our forecasting system, which we call FLARE, or Forecasting Lake and Reservoir Ecosystems, we have meteorological driver data, which are out on the reservoir. These are being pushed to GitHub. From GitHub, we're using them as driver data to run our open source lake numerical simulation water quality model, which is generating model output. We can then compare that model output with our observational data, which is streaming from sensors that are pushing to GitHub, and then together we can update our model via an ensemble common filter. This allows us to provide initial conditions for the next day of the forecast, which is fed from 16-day weather forecast ensembles from NOAA. This is then being used to generate our 16-day water quality forecast, which is first pushed to GitHub, and then second, it's being used to develop a suite of decision support tools that have been co-developed with our water utility managers with the help of several social scientists. This is sent via an email every single morning at 7:30 a.m. to our water utility managers, which is the beginning of the next day's shift. Our forecasting system successfully predicted a day of high iron water quality impairment last October, 8 days in advance. In particular, I want to show you the sample bottle on the left was a water quality sample taken the day before the high iron event. The sample bottle on the right was a surface grab the day of. So there's no way that our managers would have known that that high iron was coming if not for our forecasting system. And those 8 days in advance is a critical window for them because it gives them enough notice to be able to buy more chemicals, buy more filters, change staff schedules. They can actually preemptively respond to that impairment that's coming. So to pull this all together, we are successfully generating near-term iterative forecasts for our system. And because we're able to get this information to managers ahead of time, this results in lower utility costs, less treatment that has to happen to the water, which ultimately means less treatment and cheaper costs for the consumers of this water. Every single step of this open source forecasting system of FLARE uses tools and technology that we're hoping to scale to other sites. Specifically GLEON, our Global Lake Ecological Observatory Network sites that already have the buoy infrastructure and sensors in place. We're still very much in active development. I encourage you to go see Heather Longer's poster on this later today, and also to see our website, smartreservoir.org, where we're also publishing the forecasts every morning, and we have a wiki that talks you through some of the tools and more cyber infrastructure. The last thing I want to say is that we spent a lot of time in our project thinking about how to develop meaningful collaboration between ecologists and computer scientists. These are two disciplines that do not have a history of working closely together, and we've had to spend a lot of time thinking about how to make sure that our computer scientist colleagues felt like they weren't just the tech support. At the same time, also allowing our ecologist colleagues to learn and to try out new software that are simply, students are not being exposed to in ecology graduate programs today. And so as a result of this experience, we've developed what we refer to as an interdisciplinary pyramid for collaboration between computer science and ecologists with simple tips and techniques and suggestions that we've learned from our experiences that hopefully can advance ecological forecasting as a whole. As to call from yesterday, this is fundamentally an interdisciplinary problem, and we need to have these two communities speaking more closely together if we're going to advance our cyber infrastructure. So with that, I'd like to thank our Smart Reservoir team, the Western Virginia Water Authority, which are fabulous water utility managers who work very closely with every single day, and National Science Foundation support from the Smart Connected Communities Grant, without which none of this would be possible. Thank you.